guest JL Physics in Vangara. Today I will discuss about the mechanical properties of solids and fluids, some of important basic points. And first of all, I will special thanks to our secretary sir because he's conducting the webinar classes for intermediate students, and coordinator Swapna madam, and also Principal Srinivas Garu, and Nerala Principal Radhika Garu, and our college principal Suraka madam. Special thanks for madam. Now we'll share the class. Start now. Mechanical properties of solids. This chapter number 10, intermediate first year. Already we will discuss mechanical properties of solids. The topic covered by some of questions and important 2 marks questions and important 4 marks question also. And this day I will discuss the some of basic points and solving the problems. Mechanical properties of solids and mechanical properties of the fluids. Now here we will discuss for the first we will discuss for the now demonstrate your understanding of in this lesson elasticity, elastic limit, stress, strain, and ultimate strength. And next one, write and apply formulas for calculating Young modulus, shear modulus, and bulk modulus, and solve problems involving each of the parameters in the above objectives. Okay, now we'll enter the lesson, start the lesson. First one, elastic properties of matter. What is the elastic properties of matter? Now see here, an elastic body is one that returns to its original shape after a deformation, is called elastic body. So now see here, so we are taking some of the examples in the diagrams. First one, golf ball, second rubber band, and soccer ball. So what I'm explaining, elastic body. What is the elastic body? On one that the returns to its original shape after deformation. Deformation means when you are applied the force on rubber band or stretchable string. Okay, that force is exists the deformed that the body. So it's called as a elastic body. The next one, elastic properties of matter. Next one. So what is the inelastic body? An inelastic body is one that does not return to its original shape after a deformation. Inelastic body is one that does not return to its original shape after a deformation. For example, see here, bread and clay and inelastic ball. So these are also inelastic bodies. Now, so what is the elastic or inelastic? What is that? What is that elastic or inelastic? Now see here, an elastic collision loses no energy. The deformation of collision is fully restored. Restored is called elastic. What is inelastic? In an inelastic collision, energy is lost and the deformation may be permanent, is called inelastic. Next, what is an elastic spring? What is the elastic spring? Now see here, a spring is an example of an elastic body that can be deformed by stretching. Deformed by stretching. See here, you taken from the one of the spring, hanging some of them, attach some of the mass and hanging, then some of the force applied the mass, then the spring is extended some of the distance of x. The distance of x. Now here, what you will observe, a restoring force F acts in the direction opposite the displacement of the oscillating body. There's a principle of F equals to minus kx. Force is proportional to minus x. That is a negative displacement. Negative displacement. Now see here, we'll write down in this spring example. We will explain the Hooke's law. What is the Hooke's law? Actually, the Hooke's law is stress is proportional to the strain. Stress is proportional to the strain. But here, when a spring is stretched, there is a restoring force that is proportional to the displacement. F equals to minus kx. See here, the spring constant k is a property of the spring given by k equals to del f by del x. Del f by del x. So what's the mean del? The changes. So k equals to del f by del x. The spring constant k is a measure of the elasticity of the spring. What is the k? K is also spring constant. The spring constant is a measuring of elasticity of the spring. Elasticity of the spring. So next one. So stress and strain is a very, very important. Stress and strain. See here, stress. Stress refers to the cause of a deformation. Cause of a deformation. And strain refers to the effect of the deformation. Stress is the cause of a deformation, and strain is also effect of the deformation. Now see the spring hanging some of the mass m and stretched, some applied some of external force, and x distance moved of the spring. See here, the downward force F causes the displacement of x. The downward force F causes the displacement of x. Thus, the stress is the force. The stress is the force. The strain is the elongation. The strain is the elongation. So actually, the stress and strain, the stress are the three types of stresses: longitudinal stress, and shearing stress, and also volume stress. So three types of stresses, and strain will be also same as this. Now see here, types of stresses. We have taken the two types of stresses. That means tensile stress, and next one is the compressive stress. Tensile. So what does the tensile means? Tensile means expansion. Expansion. For example, you taken the spring. The force applied. There's the expansion. And with same example, rubber. The rubber apply the force in both sides. There's an expansion. Expansion means there's a tensile. Okay. Now here, compressive. So what does it mean by compressive? So for example, the ball compressible both sides, and spring is compressible. So the tensile means expansion, and compressive stress means then the closely compression. So now see here, a tensile stress occurs when equal and opposite forces are directed away from each other. And a compressive stress occurs when equal and opposite forces are directed towards each other. See here, W is the weight of the body, and the expansion is the tension. So F is a force, and the upside and downside is the tension. And next, another diagram, see the another diagram is the compression. Okay, now see here. Next one, longitudinal stress and strain. Longitudinal stress and strain. Now see the first of all diagram. To take one of the wire hanging on one of the rod, one of the bar, there is a longitudinal stress F by A that produces a changing in length per unit length. In such cases, see here, one of the wire, stretched wire, hanging some of the weight. There's also some of the distance is expansion of the string. The original length of the L and changing length of the string is also del L. So actually, what is the stress means? Stress is also force per unit area, F by A. Strain means per del L by L. That means changing in length by original length. Changing in length by original length. Now see here, in this the stress and strain and longitudinal strains. Give the example on the problem. See here the problem question. A steel wire 10 meters long and 2 millimeters in diameter is attached to the ceiling and a 200 newtons weight is attached to the end. So what is the applied stress? What is asking the question? What is the applied stress? So now see here, a steel wire length L equals how much length is the 10 meters of the wire, and diameter of the wire how much value? 2 millimeter. Okay, and how much force applied? How much weight applied? The 200 newtons weight is attached to the end. So finding the stress. So stress formula, what is that? Force per area. Force per area. First of all, we will finding the area. So we will finding the area principle. A equals to pi d square by 4. Pi d square by 4. That equals to pi d, that means diameter d. So this is the d equals to 0.002 meter whole square. Why? Because 2 millimeters are changing into the meters. So 0.002 meters whole square by 4. The finding that the answer A equals to 3.14. Pi means pi value 3.14 into 10 to the power of minus 6 meters. So A value is the finding. Now we are assuming the stress F by A. That means F means force. How much newtons apply the force? 200 newtons. 200 newtons by what is the area? Area A equals to 3.14 into 10 to the power of minus 6 meters. Now finding this is the answer. Stress equals to 6 point. Total calculation of 200 newtons by 3.14 into 10 to the power of minus 6. So here finding the value, stress equals to 6.37 into 10 to the power of 7 pascals. 6.37 into 10 to the power of 7 pascals. Now see here, another example. A 10 meter steel wire stretches 3.08 millimeter due to the 200 Newton of the load. What is the longitudinal strain? What is the longitudinal strain? You clearly observe. Before question is finding of the stress formula, force per area. Now this problem, finding of the strain. Strain means changing length by original length. Okay, given the above question, assuming the values of length L equals 10 meters and changing of length 3.08 millimeters, I now write the principle of strain equals to del L by L, that equals to 0.00308 meters by 10 meters. Now finding that the answer, longitudinal strain equals to 3.08 into 10 to the power of 4. Okay, are you understood? Okay, right? Now next one, the elastic limit. See here, the elastic limit is the maximum stress a body can experience without becoming permanently deformed. Once again, the elastic limit is the maximum stress a body can experience without becoming permanently deformed. See that on the rod, hang the rod is one of the rod, 2 meters of the rod hanging on the bar, and apply some of the weight W, some of expansion, and apply again more weight, again expand some of the weights, and then so what happened? See this first one where they remove the weight, So what happened? What you observe? Actually, we are taking the 2 meters of the rod, then remove the total weight. So then the body is also going on. It does not going on same position. Why? Because then you have some of small elongation, changing of the length. Okay, this is called the beyond limit. So stress equals to F by A. If the stress exceeds the elastic limit, the final length will be longer than the original. How much? 2 meters. Okay, so this is called as the elastic limit. The next one, ultimate strength. What is the ultimate strength? The ultimate strength is the greatest stress a body can experience without breaking or rupturing. Okay, see here, this is called as the ultimate strength. So how much weight you are applied, there is a without breaking. without breaking. So see here, same about the diagrams. So we are visualize the 4 diagrams. First one is the 2 meters of the wire or rod and hanging some of the weight W, some of elongation of the wire, and again applied some of the more weight and some of the large distance of elongation of the wire, and another applied the more weight. Then what happened? The string is breaking. The string is breaking. Now see here, what is the ultimate strength? Does not breaking of the wire. See here, stress equal here by A. If the stress exceeds the ultimate strength, the string breaks. The stress exceeds the ultimate strength. So what happened? The strings is break. This is called as the ultimate strength. Next one, example problem. Ultimate strength. The ultimate strength for steel is 4.89 into 10 to the power of 8 Pascal. What is the maximum weight that can be supported without breaking the wire? So what is the question asking? See here once again. The ultimate strength for the steel is 4.89 into 10 to the power of 8 Pascals. What is the maximum weight that can be supported without breaking the wire? Now see here. So assuming the values, first of all, ultimate strength 4.8 into 10 to the power of 8. This is called as the stress. F by A equals to 4.8 into 10 to the power of 8 Pascals. Now area. So what is the area? So area A equals to 3.14 into 10 to the power of minus 6. Before problem we have solved the area. So area means pi d square by 4. Pi d square by 4 area principle. Okay. So see here. Now here elongation, that means pi d square by 4 means d means diameter that we are taken from the, we're not assuming the d value, but we are taking the 2 value. So see here, the force is finding of F equals to 4.89 into 10 to the power of 8 Pascal. The force F equals to what is the stress into A. So the value, and see here F equals to force, F equals to stress means how much a value? 4.89 into 10 to the power of 8, and area how much value? 3.14 into 10 to the power of minus 6 meters. See here, this is the finding of the value 10 to the power of 8 and 10 to the power of minus 6, and point get the cancel completely, and then 4.8489 into 314. That's the calculation is 1536 newtons. Newton means force units. Okay, see that. Next one. Now we are enter the modulus of elasticity. What is the modulus of elasticity? The provided that the elastic limit is not exceeded and elastic deformation strain is directly proportional to the magnitude of the applied force per unit area. Per unit area. This is called as the modulus of elasticity. Simple thing. So what is the modulus of elasticity? Stress by strain. Stress by strain. This is called as a modulus of elasticity. The modulus of elasticity equals to what is that? Stress by strain. Now see here, the modulus of elasticity we find in one of the problem. See here, in our previous example, the stress is applied to the steel wire was 6.37 into 10 to the power of 7 Pascal, and the strain was 3.08 into 10 to the power of minus 4. Minus 4. Now see here, find the modulus of elasticity for steel. Find the modulus of elasticity for steel. Now see here, same thing on the steel rod, length L, and applied some of the weight, and the steel rod is extended some of the length. The result changing of length is the del L. Now see here, now write the principle. Modulus equals to stress by strain. That equals to stress how much value? 6.37 into 10 to the power of 7 Pascals. Strain how much value? 3.08 into 10 to the power of minus 4. So then what is the modulus? You can 10 to the power of 7 into by 10 to the power of minus 4, we can taken from 6.37 by 3.08, we are taking the 10 to the power of 9 Pascal into 207. That means 207 into 10 to the power of 9 Pascal. See here, another important point. This longitudinal modulus of elasticity is called Young's modulus and is denoted by symbol of Y. What is the Young modulus? A longitudinal modulus of elasticity is called Young's modulus. So what is the longitudinal modulus? Longitudinal stress by longitudinal strain is called Young modulus. Is denoted as symbol of the Y. So next one, see that. What is the Young modulus principle? So you see here, for material whose length is much greater than the width or thickness, we are concerned with the longitudinal modulus of elasticity or Young modulus Y. The Young modulus equals to longitudinal stress by longitudinal strain. Y equals to longitudinal stress means F by A. Longitudinal strain means changing length by horizontal length. That means del L by L. That equals to F by L by A into del L. This is the Young modulus principle. FL by A del L. See here, once again, see here, very, very important principle. Y equals to force stress. Longitudinal stress means stress. Stress means force per area. Longitudinal strain means strain. Strain means what is that? Changing length by horizontal length. That means del L by L. That equals to F by A by del L by L. That equals to FL by A del L. The units of Young modulus Pascal are 1B by in dot square. Okay now. So see here. Next one. See the one of the example problem in exam Young modulus. Young modulus question is, Young modulus for brass is 8.96 into 10 to the power of 11 Pascal. And applied a force 120 newtons, weight is attached to an 8 meter length of the brass wire. Find the increasing in length. The diameter is 1.5 millimeter. So see here, first clearly observe, first understood the problem. Young modulus of brass is 8.96 into 10 to the power of 11 Pascals. Actually here, Y equals to direct asking the principle 8.96 into 10 to the power of 11 Pascal. And apply the force, F equals to 120 newtons and length 8 meters length of brass wire. And when you are applied the 120 newtons of the force of the weight applied on the string or brass wire, then the string is some changing of length. That length is something increasing of length. So then the string diameter is 1.5 millimeter. Okay, first of all, finding that. First, find area of wire. A equals to pi d square by 4. That equals to pi into 0.0015 meter whole square by 4. We are converting the millimeter to meter. So now we'll choose the answer. Pi means 3.14 value. 3.14 into 0.0015 meter square by 4. That is the value of A equals to 1.77 into 10 to the power of minus 6 meter square. So according to Young modulus principle, Y equals to FL by A del L, or del L equals to FL by AY. Why are you taking the del L means we'll finding of increasing of length. Increasing of length means we are not assuming the value of increasing of length. We'll finding the increasing of length. What is the increasing of length? Del L. See here. Okay. Del L equals to what is the principle according to Young modulus? Del L equals to FL by AY. Okay. See here. Y equals to, same to be continue this problem. Y equals to 8.96 into 10 to the power of 11 Pascal. F equals to 120 newtons. And length L equals to 8 meters. And area A equals to 1.77 into 10 to the power minus 6 meters. Force, apply the force equals to 120 newtons. And finding of changing of length del L. Now see here. del L equals to FL by AY, and del L equals to F means 120 newtons, and L means 8 meters, and A means 1.77 to 10 to the power of minus 6 meters square, and Y means 8.96 into 10 to the power of 11 pascals. Now, this value we can calculate 120 into 8 meters, and by 1.77 into 10 to the power minus 6 and 8.96 into 10 to the power minus 7, we can calculate the increasing of length is del L equals to the maximum value of 0.605 millimeter. This is also changing of length. See here. So before problem you're finding of only Young modulus. Now this problem is asking the question is Young modulus question, but assuming the value of Young modulus, now you're finding of changing of length. Changing of length. So when you are changing of the length principle taken from the Young modulus, del L equals to FL by AY. This is a very, very important principle and problem. Now see here next one. Shear modulus. A shearing stress at least only the shape of the body. Sorry. A shearing stress alters only the shape of the body, leaving the volume unchanged. For example, see here. Consider the equal and opposite shearing forces F acting on the cube below diagram. A is on the cube, then apply the force is both sides. Now see here. See this, the cube is changing some of distance. So the shearing force F produces a shearing angle, some of the angle of changing. The shearing force F produces a shearing angle pi. The angle pi is the strain, and the stress is given by force per area as before. Okay, see here. So on the problem, calculate the shear modulus. Stress is force per unit area, F by A. The strain is the angle expressed the radians. Strain equals to pi equals to dA by L. The shear modulus S is defined as the ratio of the shearing stress F by A to the shearing strain pi. The shear modulus units are in pascals. S equals to F by A by pi. These are the shear modulus of principle. Okay. See here, let the problem. A steel stud. Stud means, for example, stud means you're taken from the nail and putting the wall. Then outside remaining point, that is also stud. Okay. The steel stud S equals to 8.27 into 10 to the power of 10 pascals and 1 centimeter in the diameter, projects 4 centimeters from the wall. A 36,000 newtons shearing force is applied to the end. What is the defection? What is the defection? D of the stud. Now see here finding out A equals to pi d square by 4 and pi equals 0.01 meter whole square by 4. And here we get the solve the A equals to 7.85 into 10 to the power minus 5 meter square. So according to the rule, S equals to shear modulus S equals to F by A by pi, that equals to F by A by D by L, that equals to FL by AD, D equals to FL by AS. Now finding the value D equals to 36,000, F means 36,000 newtons and L means the length of 0.04 meters. Now we are taking from the 4 centimeters, they are converting in the meters, 0.04 meters. Then 7.85 into 10 to the power minus 5 A value, and S is the value of 8.27 to the power of 10 pascals. Then the finding the value of answer is 0.0222 meters, 0.222 millimeter. Okay. Now see another one. Volume elasticity. So not all deformation are linear. Sometimes I apply the stress F by A results in a decreases of volume. In such cases, there is a bulk modulus B of elasticity. The bulk modulus is volume stress by volume strain. That means minus F by A by changing of volume by original value. See that. The bulk modulus is negative because of decreasing in volume. The bulk modulus is negative. Why? Because the decreasing of volume. When you are applying the force on the object, then object is changing the volume. as compressive. So you have take or expansion also and compressive. So the time you have taken from the value is negative. So this is bulk modulus is negative because decreasing in the volume V. Okay. Next, the bulk modulus equals to B equals to volume stress by volume strain, that equals to minus F by A by del V by V. Since F by A is generally pressure, force per area P, we may write B equals to minus P by del V by V, that equals to minus PV by del V. Units remains in pascals since the strain is unitless. So another problem is bulk modulus. A hydrostatic pressure press contains 5 liters of oil. Find the decreasing in volume of the oil if it is subjected to a pressure of 3000 calorie pascal. So assuming that B equals to bulk modulus equals to 1700 MPa, meter per area. Okay, M pascal. Okay. Now B equals to bulk modulus minus P by del V by V, that equals to minus PV by del V. Now see here, changing of volume, del V equals to minus PV by V, that equals to minus 3.3 into 10 to the power of 6 pascal, 3 into 10 to the power of 6 pascal into 5 liters by 1.70 into 10 to the power of 9 pascal. So decreasing in the volume V, milliliters ml, so del V equals to minus 8.82 millimeter. So once again question see here, a hydraulic press contains 5 liters of oil. Find the decreasing of the volume of the oil if it is subjected to a pressure of the 3000 kilopascals. Okay, simple thing. Changing of the volume, del V equals to, the answer is the minus 8.82 milliliters. Okay, the next one. Very, very important, Poisson ratio. So lateral contraction per unit axial elongation is called Poisson ratio. So with the elastic limit. So now see here, mu equals to del B by B by del L by L, and mu equals to del B by B by del L by L means you are taken the elasticity E. That means changing of length by vertical length. Okay, so del B equals to E into mu B. So new breadth B minus del B, that equals to B minus E mu B, and B into 1 minus B common term, B into 1 minus mu E, and since new depth equal D minus AD equals to D into 1 minus mu E. See here the diagram. Actually L is the object, is the vertical length, P is the applied force, and D is the depth, and B is the breadth. Now see here, changing of length L plus del L. So what happened? D minus changing of depth and changing of breadth. Now see here, elongation. That means the L means 1 plus E, and depth is D into 1 minus mu E, and B is the 1 minus mu E. So next see here, example, a 10 meter steel wire stretches 3.08 millimeter due to the 200 Newton load. What is the longitudinal strain? Same thing, the longitudinal strain equals to del L by L, that equals to 0.0308 meters. That means 3.08 millimeters converted to the meters by 10 m. The longitudinal strain equals to 3.08 into 10 to the power of minus 4. Okay. So next see here, another one. The ultimate strength for the steel is 4.89 into 10 to the power of 8 pascal. What is the maximum weight that can be supported without breaking the wire? One second question. The ultimate strength for the steel is 4.89 in 10 to the power of 8 pascal. What is the maximum weight that can be supported without breaking the wire? Now see here, the area of the wire A equals to 3.14 into 10 to the power minus 6, and P equals to value 4.89 into 10 to the power of 8 pascal. Now force F equals to stress into area. Okay, so F equals to ultimate strength means P value, so P into A. So you'll write the 4.8 into 10 to the power of 8 and 3.814 into 10 to the power minus 6 meter square, and F equals to 1536 newtons. The next one, another question. A piece of copper having the rectangular cross section of 15.2 millimeter into 19.1 mm is pulled in the tension with the 44,500 Newton force, producing only elastic deformation. Calculate the resulting strain, shear modulus of elasticity of copper 42 into 10 to the power of 9 Newton meter square. Now here, area A equals to, assuming the values, first of all, we have taken area A equals to 15.2 into 19.2 into 10 to the power of minus 6 meter square, and force applied for how much value? 44,500 newtons, and neta value is also 42 point, that means shearing modulus 42 into 10 to the power of 9 Newton meter square. Now we'll find out the strain equals to stress by modulus of elasticity, F by A by neta. So F equals to F by A neta, that equals to 44,500 by 15.2 into 19.2 into 10 to the power minus 6 into 42 into 10 to the power of 9. Then we can do the calculation completed. Now see here, 3.65 into 10 to the power minus 3. This question is the answer. Okay, so next one. A steel cable with a radius of 1.5 centimeters supports a chairlift at a sky area of the maximum stress is not exceed 10 to the power of 8 Newton meter square. What is the maximum load of the cable support? The answer is maximum load equals to maximum stress into cross-sectional area, that equals to 10 power of 8 Newton meter square, Newton per meter square into 22 by 7 pi value into 1.5 into 10 to the power of minus 2 meters whole square. The answer is 7.07 into 10 to the power of 4 newtons. So next one. So this is also Inhomogeneous problem. A rigid bar of the mass 15 kg supported symmetrically by 3 wires, each 2.0 meter long. Those are each end are of copper and middle one of the iron. Determine the ratio of the 3 diameters of the each is to have the same tension. See here, we are using up 3 different wires, 3 wires. So the see here, since each wire is has the same tension, therefore each wire has the same extension. Moreover, each wire has the same initial length, so strain is same for each wire. So now we write Inhomogeneous y equals stress by strain. That equals stress equals to y F by A. A means pi d square by 4 by strain, and y is inversely proportional to 1 by d square. That implies d is inversely proportional to 1 by root y. So d is a copper wire and d is a iron wire of diameter, that equals under root of y Inhomogeneous iron by Inhomogeneous copper. So what's the value of Inhomogeneous iron? 190 into 10 to the power of 9 by 110 into 10 to the power of 9 is a copper wire of Inhomogeneous. That equals under root of 10 to the power of 9, 10 to the power of 1 cancel, under root of 19 by 11, that equals to 1.314. So this is a very, very important problem. So this is MSET point of view problem. The length of metal wire is L1. When the tension is, it is F1 and L2. When the tension is F2, then the natural length of the wire is. So the one sign question, see here. The length of the metal wire is L1. When the tension in it is F1 force applied and L2. When the tension is F2, then the natural length of the wire is. See here. Let L be the natural length of the wire. For the force F1 is elongation is E1. E1 equals to F1L by AY. That implies Y equals to F1L by A E1 EL. Similarly, for the force F2, if elongation is E2, E2 equals to F2L by AY. That implies Y equals to F2L by AE2. L1 equals to L plus E1 and L2 equals to L plus E2. According to Young modulus, Y equals to F1L by A L1 minus L, that equals to F2L by A L2 minus L. Then F1 L2L L2 minus L equals to F2 L2 minus L. And F1 L2 minus F1L, that equals to F2 L1 minus F2L. Find that F common, F2 minus F1 L, that equals to L1 F2 minus L2 F1, or L equals to L1 F2 minus L2 F1 by F2 minus F1. So the correct answer is third one, L1 F2 minus L2 F1 by F2 minus F1. So important principle in this lesson: normal stress S equal to F by A, Langmuir strain del L by L, Young modulus Y equals to F by A L by del L. Breaking force equals to breaking stress into area of cross section. Volumetric strain equals to del V by V. Bulk modulus B equals to bulk stress by bulk strain, that equals to minus del P by del V by V naught. Shearing strain equals to del L by L, that is the theta. Shear modulus S equals to shear stress by shear strain, that equals to F by A by X by H. And modulus of rigid body G equals to F by A theta. And elastic potential of stretched wire equals to 1 by 2 stress into strain into volume. Thank you. So mechanical properties of solids completed. Now we are enter discuss about the mechanical properties of fluids. See here. Bernoulli equation is very, very important. The Bernoulli equation is basically conservation of energy and was derived using work energy theorem and works for fluids only. And we ignore the friction. The principle of P equals to 1 by 2 rho V square plus rho Gy is constant. Now see here. P1 plus 1 by 2 rho V1 square plus rho Gy1, that equals to P2 plus 1 by 2 rho V2 square plus rho Gy2. Now see here the Bernoulli principle diagram. Inside the flowing of the water and going in the outside the flowing of the water, the both are equal, but pressure is the heavy. Pressure is the heavy. Now see here. At constant height of H1 equals H2 and pressure P1 plus 1 by 2 rho V1 square equals to P2 plus 1 by 2 rho V2 square, or P plus 1 by 2 rho V square is constant. This may seem odd because it says as the pressure increases, the speed decreases within the fluid. Remember, high velocity and low pressure and vice versa. See here on the simple think example, water with air bubbles flow through a pipe that gets narrower. In the narrower region, the water gains speed of the bubbles. So what is that answer? Larger. Option A is the correct. Once again, question answer understood. Water with the air bubbles flow that a pipe that gets narrower. In the narrower regions, the water gains speed and the bubbles are. See this, why? Because answer is area A1 V1 that equals to A2 V2. The reason is as the water gains speed, pressure in the water decreases. In according to Bernoulli principle, decreased water pressure squeezes less on air bubbles, allowing them to expand. So that air pressure and surrounding water pressure match. If the flowing water continues its flow into a wider section of pipe, speed decreases, pressure increases, and the bubbles become the smaller. Next one. So water flows through a 1 centimeter diameter of the pipe connected to a 0.5 centimeter diameter of the pipe. Compared to the speed of the water in the 1 centimeter pipe, the speed of the 0.5 centimeter of the pipe is higher by, the answer is 4 times. Answer is the 4 times. Now see here, V1 is the velocity and V2 is the another velocity, water velocity. See that conclusion. The area of the small pipe is less. So we know that the water will flow faster there because A is proportional to R square. When the radius of reduced by 1/2, the area is reduced by 1/4. So the speed must increases by 4 times to keep the flow of rate A into V is a constant. So next, another conceptual bit. The blood flows through a coronary artery that is partially blocked by deposits of plaque along the artery wall. So what part of the artery is the volume flow of blood the largest? See here. The answer is the volume and mass flow. The volume mass flow must not change throughout, or else blood would hide with somewhere along the artery. The answer is the D. The volume flow is the same in all parts. The next one, the pressure in which the part of the coronary artery at the least. Okay, so what is that? The narrow part. The pressure will be least where the speed is the greatest. that will be in the narrow part of the artery. Bernoulli examples, the Bernoulli effect of the sheet of the paper, and then wings are designed the cause of the airflow, faster over the top of the wing, and cause of the pressure differential resulting of lift. High speed of the lower pressure and lower speed of the high pressure. Force on a roof due to the wind speed. This is also one of the Bernoulli good example. So very high speed of the air in top of the building and lower pressure, and very low speed of the force applied the inside of the building and normal pressure of the air. Roof might blow up during the hurricanes. The next one. So this is also Tarsal diagram. Fluid emerging of a hole in a container. So upside first see the next slide. Calculate speed of the water coming out. So P1 plus 1 by 2 rho V1 square plus rho G Y1, that equals to P2 plus 1 by 2 rho V2 square plus rho G Y2. We have P1 pressure equals to outgoing the pressure of P2. Both are equal, and velocity V1 equals 0 and Y1 minus Y2, that equals to H height. So rho GH equals to 1 by 2 rho V2 square, that is called V2 equals to under root of 2GH, is known as Tarsal law. So here V equals to under root of 2GH, the maximum height of the stream of water. Again, we are like Tarsal law. The speed of the efflux fluid outflow from an open tank is given by a formula identical to that a freely falling body. According to the equation of the continuity, V1 A1 that equals to V2 A2 and V2 equals to A1 by A2 V1. Since A2 is greater than to A1, so V2 equals to 0. That means the fluid is at rest, applying the Bernoulli theorem. Now see here the diagram. Another one, applying the Bernoulli theorem. P1 plus 1 by 2 rho V1 square plus rho G V1, that equals rho G Y1, that equals to P2 plus 1 by 2 rho V2 square plus rho G Y2. P1 equals to PA, atmosphere pressure, Y2 minus Y1 equals to H, and PA plus 1 by 2 rho V1 square plus rho G Y1, that equals to P plus rho G Y2. So V1 equals to under root of 2GH plus 2 into P minus PA by rho, when pressure is greater than the pressure of atmosphere, and therefore V1 velocity equals to under root of 2GH. This is a Tarsal law. And venturimeter is the gauge used to measure the rate of flow of fluid when the fluid is steady, speeded the constriction. So V2 equals to A by A V1 according to Bernoulli equation. P1 plus 1 by 2 rho V1 square equals to P2 plus 1 by 2 rho V2 square A1 by A2 whole square. P1 minus P2 equals to rho GH, that equals to 1 by 2 P rho V1 square into A1 by A2 whole square minus 1. So V1 equals to under root of 2GH, A1 by A2 whole square minus 1. Speed of the fluid at the wide neck. Reynolds number is a very important, venturimeter and Reynolds number. When the rate of flow of the fluid is large, the flow becomes turbulent. Turbulent means zigzag flowing of the water. Turbulent means. An obstacle placed is the path of the fast moving fluid causes turbulence. The Reynolds number is the implies the flow would be turbulent or not. R E equals to rho VD by neta. R rho is the density of fluid and D is the dimension of pipe, and V is the speed of fluid flow, and neta is the viscosity of the fluid. RE is dimensionless. Reynolds number is dimensionless. R is less than 1000 streamlines of laminar flow. 2000 is greater than, Reynolds number is greater than to 1000 unsteady flow, and Reynolds number is greater than 2000 turbulent flow. The Reynolds number is ratio of initial force to viscous force. Use turbulence promotes mixing, increasing the transfer rate of masses, momentum, and energy. And pressure of the depth. Pressure of the depth. Consider pressure at point of 1, see that the diagram, P1, and point of 2, P2 pressure, and mass of fluid inside the cylinder M, and area of the base of the cylinder A, height of the cylinder H, and density of fluid rho. So what is the rate the principle? P2 minus P1 equals to mg by A. M is the rho HA and P2 minus P1 equals rho GH. When a point 1 is open to atmosphere, P1 equals to atmosphere of pressure and P2 equals to absolute pressure. P equals to PA plus rho GH. This is called as a gauge pressure. Gauge pressure P minus PA equals to rho GH. Some of the important points in the 2 marks bits. The glass surface angle of contact is less than 90 degrees, so water drops with the lotus leaf. Lotus leaf angle of contact is greater than 90 degrees, so water drop does not wet the lotus leaf. Due to surface tension, raindrops and water bubbles are spherical in nature, and excess pressure in a liquid drop equals to 2s by r. Air bubble excess pressure is 2s by r. Why? Because both are only one inner surface, and soap bubble excess pressure is 4s by r. Why? Because these are two surfaces. That means 2 into 2s by r, that equals to 4s by r. So this is very, very important points. Thank you.